about the slope deflection method. Slope deflection method is studied in analysis of indeterminate structures. It is a very simple method. Once you understand the procedure and basic concept, then you can solve n number of problems. The slope deflection method, it was first presented by Professor G.A. Maney in the year 1915. And in this method, the joints are considered to be rigid. This is very important, that the joints are considered to be rigid. That is, the joints rotate as a whole and the angles between the tangents to the elastic curve meeting at a joint do not change due to deformations. Okay, the joints are rigid means what? That the joints are rotating as a whole. Okay, then the rotations of the joints are treated as unknowns. So what is the main aim of using slope deflection method? What we are going to find here are the rotations, that is represented by theta. Okay, so the rotations are the unknowns, and what we are doing, we are writing a series of simultaneous equations. Okay, a series of simultaneous equations are written to find the unknown rotation values. Okay, so if this is a beam A, B and C. Okay, so theta B and theta C both will be unknown. So to find two unknowns, that is rotation at B and rotation at C, we need two simultaneous equations. So we will write the simultaneous equation and then we will find the unknown rotation values. Okay, the solution of the slope deflection equations along with the equilibrium equations. It gives the values of unknown rotations of the joints. Knowing these rotations at the end, the moments will be calculated. Okay, so that is moments means MAB, MBA, MBC, MCB. These are the final moment values are calculated after finding the rotation values. Okay, then we will draw the shear force diagram and bending moment diagram. So before we go into problems, important is knowing about the sign conventions. So sign conventions are very important. First one is the clockwise fixed end moment is taken as positive. Clockwise fixed and moments are taken as positive, and the anti-clockwise fixed end moment is taken as negative. Anti-clockwise fixed end moment are taken as negative. So we are supposed to know the sign conventions first. Then next is a clockwise rotation or slope is taken as positive. Clockwise rotation or slope is taken as positive, and anti-clockwise rotation or slope is taken as negative. Then in certain cases there will be the settlement of the joints. Okay, so if one end of beam settles, the settlement or sinking, the settlement or sinking or deflection is taken as positive, is taken as positive if it rotates the beam, if it rotates the beam as a whole, as a whole in clockwise direction, and it is taken as negative, and it is taken as negative, that is the settlement or deflection, if it rotates the beam, if it means what? The settlement. If it rotates the beam as a whole in anti-clockwise direction, means we can see here, I'll just show you. Suppose a beam is fixed here, hinged roller supports are there. Here there is settlement or sinking or deflection. Then at fixed end there will be no sinking, so it will deflect or settle or sink. This is called as delta. Okay, so what it is making, it is deflecting here. The axis of beam is going down like this. So from axis of the beam you have to go towards the sinking or settlement. Then what it will be? It will be a clockwise. If it is in a clockwise direction, then it is taken as positive, that is the delta term. Okay, then if it is going like this, then from axis of beam, if we go like this, then there is the sinking or settlement, that is anti-clockwise direction, then delta is taken as negative. That is what this sign convention explains. Okay, next, slope deflection equations. Slope deflection equations. First, let us take a beam like this. Suppose take any loading, there is a UDL. Then the fixed end moments here, if this is A, this is B, then MFAB, and this is MFBA. In one of my videos I have explained how to find the fixed end moments for various cases. As and when I will solve the problems, I will be explaining how to find the fixed end moments. I will put the link of that video in the description box. You can go through that video for various cases how to find the fixed end moments. Then okay, here there will be no sinking or settlement. Okay, and a tangent here, then this will be theta A, right? And this is the moment value 4EI theta A by L, and this is 2EI theta A by L. We are writing the slope deflection equation. These equations are universal. For any problem, you have to use the same equation, putting the conditions according to your given numerical problem. Okay, so suppose it is deflecting like this, then here this is theta B at B. Okay, then this will be 4EI by L theta B and 2EI theta B by L. Then the rotations, elastic curve, then now sinking, if it is represented by term delta usually, then induced moment, that is 6 ei delta by L square, and here 6 ei delta by L square. Now the slope deflection equations, total moment values, the total moment value to find the moments. First is MAB equal to plus or minus MFAB plus 2EI by L 2 theta A plus theta B minus 3 delta by L. Okay, I have added these terms and simplified. You will get the same equation. MBA equal to plus or minus MFBA plus 2EI by L 2 theta B plus theta A minus 3 delta by L. Okay, MFAB, MFBA are nothing but fixed end moments. Okay, theta A, theta B are the rotation values or slope values. Delta is the amount of settlement. L is the span considered. Okay, now I'll explain how to solve the problem and what are the steps. Okay, so the slope deflection method, always the steps will be, step 1, what we have to do is we have to calculate fixed end moments. That is the first step. Then step 2 is for each span we have to write the slope deflection equations. Slope deflection equations we have to write. Then step 3 is the writing joint equilibrium conditions. What are joint equilibrium condition? A, B, C. For this, at joint B, two members are meeting, that is ABBC. So at joint B, joint equilibrium condition means MBA plus MBC equal to 0. This is the joint equilibrium condition. So after writing slope deflection equation, we have to write the joint equilibrium condition, writing these equations in this, substituting in the joint equilibrium condition. Then in this step we will get the slope values or rotation values. Then last step is final moments. You have to substitute those slope or rotation values and find the final moment. Here we will be getting all the slope deflection equations, that is moment equations. Once you get rotation values, substitute and get the final moments. Then step 5, you have to draw the shear force diagram, bending moment diagram and elastic curve. So if you follow these 5 steps, okay, every problem it is same. Every problem you have to follow the same procedure. Okay, it is very simple. I'll explain with one example today. Let us consider here analyze the continuous beam shown by slope deflection method. Slope deflection method and draw shear force and bending moment diagrams. Okay. First, as I said, let us see what is the given beam. It is fixed at A and at C, and here B hinged support. There is a UDL. It is 10 kilonewton per meter, and there is a point load of 60 kilonewton, 3 meters, 3 meters. It is 6 meters. First, step 1, let us calculate the fixed end moments. Calculation of fixed end moments. Span wise we have to do always. For span AB, MFAB equal to minus WL by 8 minus 60 into the span, 3 plus 3, 6. So 60 into 6 by 8, which is equal to 45 kilonewton meter. Then MFBA is equal to plus WL by 8. This is the formula to find fixed end moment when there is a single central point load over a span. So plus WL by 8 means 60 into 6 by 8. This is minus 45 kilonewton meter. It is plus 45 kilonewton meter. Then span BC. In span BC, there is a UDL. Okay, so for UDL, fixed end moment MFBC is equal to minus WL square by 12. So minus 10 into 6 square by 12. It is minus 30 kilonewton meter, and MFCB is plus WL square by 12. So 10 into 6 square by 12, it is plus 30 kilonewton meter. So now for both the spans we have written the fixed end moment values MFAB, MFBA, MFBC, MFCB. Then step 2. What is step 2? Is writing slope deflection equations. First we have to note down what are the conditions here. Here we have seen that A and C both are fixed ends. So there will be no delta or settlement or sinking, and it is given there is no settlement and sinking, and the rotations will be 0 at A and C since they are fixed. So we have to just write that is delta is 0, that is no settlement or sinking. It is not given in the problem that any end is sinking or settling, and the rotation values theta A is 0, also theta C is 0 because they are fixed ends. Now for span AB, let us write the slope deflection equations. MAB equal to 2 EI by L to theta A plus theta B minus 3 delta by L plus or minus MFAB, which is equal to 2 EI by span AB, length is 6 and theta A is 0, delta is 0, so theta B, and MFAB value it is minus 45. So on simplification we can write that 2 ei theta b by 6 minus 45, it is 1. Next, once we write MAB, then we can write MBA equal to 2 ei by L 2 theta b plus theta a minus 3 delta by L plus or minus MFBA. So 2 ei by 6, 2 theta b, theta a is 0, delta is 0, plus 45. So 4 ei theta b by 6 plus 45, it is equation 2, MBA. Then span BC, MBC equal to 2 ei by L 2 theta b plus theta c minus 3 delta by L plus or minus MFBC, which is equal to 2 ei by BC. Its length is 6, theta b 2 theta b, theta c is 0, delta is 0, minus 30. 4 ei theta b by 6 minus 30, it is equation 3. Then MCB 2 ei by L 2 theta c. How to remember, right? First, there is a term c, so you have to write 2 theta c plus theta b minus 3 delta by L. Here you can see BC means 2 theta b plus theta c, okay, like that, plus or minus MFCB, which is equal to 2 ei by 6, theta c is 0, delta is 0, theta b plus 30, which is equal to 2 ei theta b by 6 plus 30. It is equation 4. So now we have written all the 4 slope deflection equations. Okay. Once we write slope deflection equation, then next is joint equilibrium condition. Step 3. Joint equilibrium condition. So joint equilibrium condition, as I explained here, we can see that there is a joint B here. So MBA plus MBC equal to 0. So let us write the joint equilibrium condition. MBA plus MBC equal to 0. Substitute MBA equation. What we have got? 4 ei theta b by 6 plus 45 plus 4 ei theta b by 6 minus 30 equal to 0. Okay. On simplification, what you get here? 4 ei theta b by 6, 4 ei theta b by 6. Okay. So it will be 2 times 4 ei theta b by 6 plus 45 minus 30, it is plus 15 equal to 0. Then ei theta b equal to minus 11.25 on simplification. Therefore, theta b equal to minus 11.25 by ei. So now we have got the unknown rotation value at joint B, theta b. Now next step is simple, just substitute the rotation value in the final moment. So fourth step, that is slope deflection equations, final moments. Already we know slope deflection equation MAB equal to 2 ei theta b by 6 minus 45. 2 ei by 6 theta b is minus 11.25 by EI minus 45, which is equal to minus 48.75 kilonewton meter. Then MVA equal to 4 EI theta B by 6 plus 45. So 4 EI by 6 into theta B is minus 11.25 by EI plus 45, which is equal to 37.5 kilonewton meter. Now we got MAB, MBA values. Next is MBC is equal to 4 EI theta B by 6 minus 30, which is equal to 4 EI by 6. Theta B value is minus 11.25 by EI minus 30, which is equal to minus 37.5 kilonewton meter. Then MCB equal to 2 EI theta B by 6 plus 30. 2 EI by 6 theta B is minus 11.25 by EI plus 30 is equal to 26.25 kilonewton meter. Now we have got all the moment values, final moment values. I also undertake the online tuitions. If anybody is interested, you can contact me. Please like, share and subscribe to my channel. Online tuition classes for all civil engineering subjects of all semesters. You can contact 9353709165. You can WhatsApp me. So next is drawing the shear force diagram and bending moment diagram. Considering the free body diagram, of span AB. $60 kilonewton, 48.75, 3 meters, 3 meters. This is B, this is A. So it is 37.5 kilonewton meter. This is RA. Now taking moment about point A, MA is equal to 0. Okay. This is how we draw the free body diagram of span. We will take two spans separately, that is AB and BC. And we will write the final moment values what we have got. This is MAB and this is MBA. Okay. Now, if we take moment about point A, this is RB, reactions at A and B. First, about point A, if you are taking, then the moment due to this 60 kilonewton, it will cause a clockwise moment about A. So 60 into 3, and this is also clockwise moment, that is 37.5. So plus 37.5. The moment due to reaction RB, okay, about point A, it is anti-clockwise. So minus RB, the distance of RB from A, it is 3 plus 3, 6. Minus 6 RB. And this is also anti-clockwise, minus 48.75 equal to 0. Therefore, on simplification, RB equal to 28.125 kilonewton. All this, why we are doing this to just draw the shear force diagram. Once we get all these reactions, we can draw the SFD. So we are doing this. Then summation of vertical forces equal to 0, that is sigma Fy equal to 0 or sigma V equal to 0. RA plus RB equal to 60. RB we have got 28.125. So RA equal to 60 minus 28.125, which is equal to 31.875 kilonewton. RA, RB value we got. Next, considering the span PC, considering free body diagram of span BC. Okay, here C, it is B, this is UDL, it is 10 kilonewton per meter, and span is 6 meters. Okay, the reaction at B, let us say it is RB, at C it is RC. Okay, taking summation of moments about point B equal to 0. First, this UDL will cause a clockwise moment, 10 into 6 into 3 clockwise. Then we have to write the moment values. MBC value, it is 37.5 and it is 26.25 MCB. So UDL is causing a clockwise moment about B. This is also clockwise moment plus 26.25. RC will cause an anti-clockwise moment about point B like this, right? So minus, it is the distance is 6 meters. So minus 6 RC, and this is also anti-clockwise, minus 37.5 equal to 0. Now on simplification, RC equal to, we get 28.125 kilonewton, and taking summation of vertical forces equal to 0 or sigma Fy equal to 0, what we get, RB plus RC equal to 10 into 6, that is intensity of UDL into the span over which it is spread, that is 60. RC is RB plus 28.125 equal to 60. Therefore, RB equal to 60 minus 28.125. We get RB equal to 31.875 kilonewton. Okay. Just check. Let's say just 60 minus 28.125, we are getting, yes, 31.875 kilonewton, right? So once we get these reactions, now we can draw the shear force diagram, bending moment diagram. Okay, so ten kilonewton per meter, 3 meter, 3 meter, it is 6 meters. Okay, let us draw the free bending moment diagram and the shear force diagram for this. Yes. This is free bending moment diagram. First, the moment value MAB. What we have got, MAB value is minus 48.75. So minus means it is anti-clockwise, pushing the beam up like this. So we will represent it like this, 48.75. And at B, that is MBA. MBA is 37.5. 37.5. Here it is 37.5. Okay. Due to this 60 kilonewton point load, due to this, what will be the bending moment diagram? It is WL by 4. We all know WL by 4 is the formula. W is 60. 60 into 6 by 4. Right? So we are getting 90 kilonewton meter. Now Here due to UDL, WL square by 8. Okay, WL square by 8. 10 into 6 square by 8. So it is 45 kilonewton meter. Like this, it is parabolic, we all know, 45 kilonewton meter. Okay, and MCB value is 26.25. 26.25. So it's going to join like this. Just shade this portion. Your free bending moment diagram looks like this. This is how we draw the free bending moment diagram. Now next is shear force diagram. Shear force diagram. First values, RA value, what we have got, RA value is reaction 31.875. So 31.875. Then it will be constant till under this 60 kilonewton. So 31.875 minus 60. It will be minus 28.125. Then RB. RB value is the one which you have found out for span AB. That is 28.125. So we will be reaching till here. Okay. Then the RB value which we have found for span BC. How much it is? RB value 31.875. So moving upwards plus 31.875. Right. Then 31.875 minus, okay, minus 10 into 6. So we have to subtract this UDL, 10 into 6. So 31.875 minus 10 into 6. How much we are getting? We are getting minus 28.125. Then next, the RC value we have got plus 28.125. So from minus, if we now add that value, RC value, we will reach the axis of the beam, this line. So your shear force diagram, I hope all of you understood how to draw the SFD, okay, and free bending moment diagram, and all the slope deflection method. If I hope all of you have understood. If you have any doubts, please mention in the comment section, and if anybody is interested in the online tuition classes, you can contact me. And whichever topic is of your interest, if you are not understanding any topic, then you can mention in the comment section. I will prepare a video and upload for the same topic. Okay, please like, share and subscribe to my channel. Thank you.